The atom was supposed to be permanent. That's not a poetic way of putting it. That was the actual working assumption of every physicist alive in 1895. The word atom comes from the Greek. It means uncuttable, indivisible, the end of the line. You could break molecules apart into atoms, but the atom itself, that was the floor. Solid, stable, unchanging. The thing underneath everything else. Uranium didn't get the memo. It's been quietly disproving that assumption for 4.5 billion years. Before this planet had oceans. Before the first living cell divided. Before anything we'd recognize as history. The atom was supposed to be permanent, and uranium just kept doing what it does, shedding pieces of itself, transforming, radiating, completely indifferent to what the textbooks said. Here's the thing I want you to hold on to from the start. We didn't discover radioactivity in 1896. What we did in 1896 was finally build instruments, sensitive enough to notice something that had been running without us. The process didn't begin when we found it. It didn't change when we named it. We just walked into a room where something enormous had been happening for longer than the Earth has existed, and we finally had a device that could pick up the signal. That reframing matters, because what I'm going to show you today isn't a human invention or a modern danger. It's something older than biology itself. And if you want to understand what uranium actually is, not the symbol, not the warning sign, the physical thing, you have to start there. I want to tell you about a rock. Pitchblende. Dark, heavy, dense ore, completely unremarkable to look at. The kind of sample you'd walk past in a mineral collection without a second glance. Pierre and I were measuring the radiation coming off it in our laboratory in Paris. A shed, really, with a leaking roof and no proper ventilation. Cold enough in winter, but we worked in our coats. We ran the numbers on how much radiation the pitchblende was producing, and the numbers were wrong. Not slightly off, not a rounding error. The uranium content alone couldn't account for what we were measuring. The excess was too large, too consistent, too stubborn to be instrument error. We checked again, same result. Checked the instruments, same result. The math kept breaking in exactly the same way. Most people, when the numbers don't work, go back and check their arithmetic. That's reasonable. That's what you're supposed to do. I went looking for whatever was producing the extra radiation, because if the math is consistently wrong in the same direction, the model is missing something real. The math wasn't lying. The model was incomplete. That instinct, not I made a mistake, but something is here that I haven't accounted for. That's what led to radium, to polonium, eventually to 2 Nobel Prizes in 2 different sciences, which I understand is considered unusual. But more than any of that, it led to a question nobody had seriously asked before. Where is this radiation actually coming from? Not from a chemical reaction, not from heat or light or anything external. From inside the atom itself. From something the atom was doing on its own, continuously, without any trigger from the outside world. That broke the model. Not bent it, broke it clean. So let's go inside and look at what's actually happening. 92 protons, packed into a nucleus so small that if you lined up 10 million of them in a row, they'd barely span the width of a single human hair. That's the scale we're talking about. And inside that almost incomprehensibly small space, every single one of those protons carries a positive charge. Same sign, positive. And positive repel each other. That's not a suggestion, that's electromagnetism. one of the most reliable rules in all of physics. Put two protons near each other, and they push apart with real force. Now put 92 of them together, crammed into a space smaller than anything you can see. And you've got 92 protons all pushing against each other simultaneously, constantly, with enormous electromagnetic force. And they don't fly apart. Why? The strong nuclear force. It doesn't get talked about much outside physics classrooms, but it is by a significant margin the most powerful force in nature, roughly 100 times stronger than electromagnetism. At very close range, it grabs protons and neutrons and holds them together with a grip that overwhelms the electromagnetic repulsion completely. The catch is range. The strong force only works at contact distance. Distance is smaller than the nucleus itself. Think of two people in a crowded room holding hands. As long as they're touching, the grip holds. Move them to opposite ends of the room. The grip is gone entirely, but they can still shout at each other across the space. That's the difference between the strong force and electromagnetism at uranium scale. The shouting, the electromagnetic repulsion, reaches across the whole nucleus just fine. The grip requires contact. In small atoms, this works without a problem. The nucleus is compact enough that the strong force covers the whole thing comfortably. Everything's close enough to everything else. Uranium's nucleus is not small. It's the largest nucleus that forms naturally on Earth, and even it is barely stable. Protons on opposite ends of that nucleus are far enough apart that the strong force between them has nearly vanished. The electromagnetic repulsion, though, still reaching across, still pushing, still winning at the edges. The nucleus is under permanent physical tension, an ongoing argument between two forces with different ranges. And uranium is sitting right at the edge of where that argument can be maintained. Radioactive decay is what happens when the nucleus finally loses a small piece of that argument. It ejects something, sheds mass and energy, and settles into something slightly more stable. It does this over millions of years. Patient, incremental, inevitable. Now what actually comes off that nucleus, and what does it do when it reaches you? Three things. And I want to be direct about this. They are not three versions of the same problem. They are three completely different physical events, and treating them as interchangeable is the kind of oversimplification that gets people hurt. Alpha particles first. 2 protons, 2 neutrons, essentially a helium nucleus moving through space. They're heavy and slow. A sheet of paper stops them. Your skin stops them. People hear this and relax. That's a mistake. Get an alpha emitter inside your body. Inhale it, swallow it, absorb it through a wound, and the physics flips completely. Inside tissue, the alpha particle can't spread out. It dumps its entire energy into a tiny concentrated area, point-blank range against living cells. The damage per track is enormous. Alexander Litvinenko was a former Russian intelligence officer living in London. In 2006, someone put polonium-210 in his tea. Polonium is an alpha emitter. His doctors spent days running tests for every conventional poison they could think of. Nothing. The alpha particles never needed to penetrate anything. They were already inside him, firing at point-blank range into his gut lining, his bone marrow, his organs. He was dead in 23 days. The diagnosis only came after, when radiation detectors found contamination trails across half of London. Distance is everything with alpha particles. Remove the distance, and you've removed the only protection. Beta particles are different. These are electrons, fast ones, ejected from the nucleus when a neutron converts into a proton. They can push through skin, reach a centimeter or two into soft tissue. Less concentrated damage than alpha, more geographic coverage. Then gamma rays, no mass, no charge, pure electromagnetic energy. They go through you the way light goes through glass, except they leave something behind on the way through, a trail of ionization. That word ionization is the entire story. Everything else I've said is context for this. Your DNA is held together by electron bonds, that long, precise, extraordinary molecule inside every one of your cells, the one carrying the instructions for every protein your body makes, is held together by specific arrangements of electrons. When radiation passes through you and strips electrons from the atoms along its path, it destabilizes those bonds. Breaks occur. Sometimes a single strand breaks. Your cells handle that constantly. They've been doing it since the first complex life evolved. It's normal cellular maintenance. But sometimes the radiation causes a double strand break. Both helices simultaneously close together. And the repair enzymes that scan your genome looking for damage, they evolved reading single strand breaks. Double strand breaks confuse them. They sometimes misread the break site. They occasionally stitch the wrong ends together. When that repair fails completely, the cell dies. That's actually the better outcome. A dead cell doesn't divide. It doesn't carry a corrupted instruction into future generations of cells. The dangerous outcome is when repair almost works. The cell survives, but survives with a rewritten gene buried in its genome. That cell keeps dividing, copies the error into every daughter cell. If those copied errors accumulate in the genes that govern when a cell divides and when it stops, the cell loses the off switch. It grows when it shouldn't. That's cancer, not something foreign attacking you. Your own cells running a program that's been quietly rewritten. We can map every protein involved in that repair process. We know the names, the structures, the sequences. What we cannot do is predict which repair, in which cell, in which person will fail. Same tissue, same dose, different people, different outcomes. The system is understood, the individual is not. That gap is real and it hasn't closed. Here's something that almost never gets mentioned. Uranium doesn't decay once and stop. It decays through 14 steps. Uranium becomes thorium. Thorium becomes protactinium. That becomes radium, then radon, then polonium, then bismuth, then lead. Each step is a new element with its own half-life, its own radiation signature, its own level of biological danger. Radium is roughly 1,000,000 times more radioactive per gram than uranium. I isolated it, spent 4 years processing tons of pitchblende in that leaking shed to get 1/10 of a gram. People think of radium as something I created. It isn't. It's what uranium becomes after millions of years of decay. Geological time did the chemistry. I just had the instruments to find it. Radon is the one that should concern most people right now. Colorless, odorless, a gas that seeps up from uranium-bearing soil into basements, accumulates in enclosed spaces, and gets breathed in without any warning at all. It's the second leading cause of lung cancer in the United States. Nobody chose to encounter it. It was just there, produced continuously by uranium that's been in the ground since before this continent existed. And the end point of all of this, after billions of years of transformation, 14 steps of decay, through elements that didn't exist until uranium created them. The chain ends in lead. Ordinary, stable, unremarkable lead. Something you'd use for a fishing weight. That's what uranium becomes. Given enough time, the chain is running right now, in the ground under your feet. It was running before the first human beings stood upright. Now I need to tell you something that should unsettle you more than it usually does. We can predict with extraordinary precision how many atoms in a sample of uranium will decay over the next 10,000 years. The statistical behavior of large populations of nuclei is beautifully well described. We can calculate half-lives to multiple decimal places. The math is precise and reliable. We cannot tell you when any specific nucleus will decay. Not within a century, not within a year, not at all. The answer is genuinely, physically random. And I don't mean random the way a coin flip seems random because you can't track every variable. I mean truly, fundamentally undetermined. Quantum mechanics, our deepest, most carefully tested description of physical reality, says the outcome doesn't exist before it happens. There's no hidden clock inside the nucleus counting down, no predetermined moment. It decays when it decays, and nothing in current physics can change that answer. Think about what that means sitting next to everything else I've described. We understand the system well enough to build reactors, calculate binding energies, design medical imaging devices that use radioactive isotopes to see inside living bodies. We cannot tell you which atom goes next. The engineering works. The deepest explanation is still missing. I spent my career building precision into measurement. The more precise my instruments became, the more clearly I could see the edge of what precision could reach, and what existed past that edge. Unreachable not because the instruments weren't good enough, but because the universe appears to be genuinely undetermined at that scale. Uranium-238 has a half-life of 4.5 billion years. That number is approximately the current age of the Earth. It was decaying before this planet had liquid water on its surface, before the atmosphere had free oxygen, before the first molecule figured out how to copy itself. It will still be decaying when every language humans have ever spoken is not just forgotten, but entirely unrecoverable. When there is no one left who remembers there were languages. We stumbled into this. Built instruments sensitive enough to notice a process that had been running for 4 billion years without us, named it, measured it, and then, in less than 50 years, split it, weaponized it, and used it to end a war. 50 years from first detection to Hiroshima. That's how fast the distance between discovery and consequence can close. The radium girls painted their teeth to glow at dances. They were told the paint was harmless. I carried radium in my coat pocket for years, handled polonium with bare hands in a cold laboratory, with no real ventilation. The Chernobyl workers walked into the reactor building without being told what the dosimeters already showed. In each case, the danger was completely real and completely invisible. Not because anyone was reckless, but because the knowledge didn't exist yet, or existed somewhere and didn't reach the people in the room. Every generation believes it's finally drawn the line in the right place. Sometimes that's true. The gap between what we know and what we're confident we know, that gap has consequences, and it doesn't announce itself. What uranium actually shows us, if you follow it all the way down, is that matter is not static. It changes. Spontaneously. Irreversibly. The nucleus doesn't know we're here. It doesn't adjust for us. doesn't slow down for our safety standards or speed up for our reactors unless we force it to. It just keeps losing its internal argument, one particle at a time, at a rate that was set before the planet cooled. We named it, we measured it, we split it. We built cities on the energy it releases, and we leveled cities with the same energy, sometimes within the same decade. We put people downwind of test sites and paid their families settlements 30 years later. The element is unchanged by all of this. We named radioactivity. We did not finish understanding it. And the distance between those two things, between what we can label and what we can actually explain, that distance is still enormous. It doesn't shrink just because the labels have gotten more precise. That's not a reason to stop. It's the shape of what real inquiry looks like from the inside. Not a march toward complete answers, but a progressive, honest mapping of what's knowable and what at the deepest level apparently isn't. The nucleus keeps losing its argument. We keep trying to understand why. Neither of us is finished.